Alright, welcome back to Physics 11, and in this video we're going to be looking at potential energy. Now we already talked about energy and how we can do work with energy. So if you remember your grade 10 science, energy cannot be created nor destroyed, it can only be transferred or transformed. So let's take a look at potential energy, how we can use that to transfer energy from stored energy to actually doing work. So potential energy, as kind of the word implies, potential has the potential to do work, and this is the stored energy of something. And we can store it in different ways. For example, one of them is elastic potential energy. So think of like a spring. A spring can be either compressed, right? So you have to put in energy first to compress it, and then once you release it, it will release some of that potential energy. Or you can also stretch it, and then once you release it, it'll compress back to its original shape, and again, at the same time, it will release some of that stored energy. But there's other examples that use elastic potential energy, for example, elastic bands, like bungee cords, or let's say bow and arrow, right? Bow is basically a spring as well. So anything that bends has the potential to be used as a storage for potential energy, unless it breaks, of course, then it's not going to work. Also, compressed air that's an example of storing potential energy. You can compress the air, and then when you release it, it can do work. So same thing goes for water. You can store the water and then release it. So that's one of the ways we can actually use wind energy in combination with hydro energy to constantly put out electricity. So anyway, another example of potential energy is chemical energy. And the most common example for this is food and batteries and, for example, fossil fuels, right? So whenever you eat, your body will digest the food, break it down, and then you have the energy to do work. Same thing with batteries. For example, when you take Chem 12, you're going to learn about redox equations. You're going to learn how batteries work. And for example, gasoline is a really good source of energy, has really high density of energy, and that's one of the reasons we keep using it today. We haven't really found a good substitute for it. So these are examples of potential energy that are stored in chemicals. So basically, once you break it down, then you can release the energy. Another way you can store energy is through a static charge. So an example of this would be when you see a lightning strike the ground or a tree or something like that. So basically what happens there is that the clouds accumulate a static charge, and at some point they'll release it and they'll go down straight to the closest grounded point. So another example I can think of, if let's say you rub your feet on a carpet and then you zap your sibling as they come by because you accumulated charge on your body by rubbing the feet on the carpet, and then you can release it to someone who's grounded. Or let's say if you touch something metal that's grounded, you'll feel the zap yourself. So that's an example of potential energy that's stored as a charge. So you have three examples: chemical, elastic, and electrical. Now in our class, we're going to be mostly talking about gravitational potential energy. So this is going to be dependent on the position of the object compared to some reference point. So gravitational potential energy is energy that's stored due to its position about the Earth, so about the surface normally. So for example, here we have the Olympic weightlifter, and as she lifts that weight, now that weight has potential energy. So when she releases it, some of the energy will get released. So again, there's a reminder here: energy can be converted into different forms by doing work. And this is really going back to the first law of thermodynamics, that energy cannot be created nor destroyed, can only be transferred or transformed. So energy can be transformed, and as it gets transformed, it can do work. Now, of course, in real life, there's some losses of energy due to like sound, friction, heat, all of that. But in our case, we're going to be simplifying things and just assume that at least at these first few examples, we're not going to be dealing with heat losses. So work converts energy into different forms. So here we have an example. Let's say we have this boulder on a cliff about Wile E. Coyote. So the boulder has the potential energy due to its position. So for example, if it drops, it can crush him, right? So if it was just sitting on the ground, then it wouldn't do anything. So in this case, the boulder only has the potential to fall because of its elevation. If it was sitting on the ground, then it would not be able to do any work. So if you look at the potential energy equation, you're going to notice that it's the mass times the acceleration due to gravity times height, which is really the same equation that we saw when we talked about doing work against gravity. And that's actually one of the ways that we can derive this. So again, we're going to use E for energy, subscript P for potential energy, because we're going to be looking at other types of energy like kinetic energy and elastic energy. And for example, you can come up with other subscripts to describe other types of energies. So let's see. Again, this is just a reminder that this is the same formula that we used for work done against gravity. Now, whenever you make a diagram or you describe a problem, the potential energy of something is always going to be measured relative to some reference point. So for example, we can think of the ground as a reference point, or the tabletop as a reference point, or the sea level as a reference point. So let's take a look at this example. We have this 15 kilogram textbook, let's say it's a giant encyclopedia or something like that, and it's sitting on a 1.2 meter table, and if the book is lifted 0.8 meters above the table, how much gravitational potential energy does it have? So are we talking about here, is it with respect to the tabletop or is it with respect to the floor? So we can do two calculations. First, let's figure out what's the potential energy of this book with respect to the tabletop. So maybe this is like some sort of a lab bench or something. So in this case, we're going to make a little diagram here on the side. So let's say we have our table right here, right? And we know that this distance is going to be 0.80 meters, right? And here's our textbook. So in this case, our H value is going to be 0.8, right? So we're going to use the potential energy equation, E subscript P equal to M for mass, G for acceleration due to gravity, and height. So we're going to plug in our values. The mass is 15 kilograms, so 15.0, so 3 sig figs. And then we have 9.8, which we're going to treat as a constant, and multiply by the height of 0.8. So our answer should have 2 sig figs because, again, 0.8 has 2 sig figs. So in this case, if you multiply this together, you will end up with 120 joules. So remember, energy is measured in Newton meters or joules. So this is going to be 120 joules. So that's our potential energy of the textbook with respect to the tabletop. But what if we ask, what about the potential energy with respect to the floor? Let's say if you were to drop it, not to the table on the tabletop, but on the floor. In that case, we have to add the height of the table plus the height that you lifted above the table, and then use that as our height in our equation. So in this case, the formula is going to be exactly the same. We're going to use the M times G times H, but the only difference in this case is that we're going to plug in a different height. So here we're going to add the two heights. So 0.8 meters and 1.2 meters, that's going to be 2.00 meters in total. So we can add it here, or you can add it as a separate calculation. So let's do it here. So it's 1.20, so 2 decimals. So we need to add 2 decimals. So we're going to end up with this, 15.0 times 9.8 times 2.00, so 3 sig figs there. So in this case, when you multiply this together, we're going to end up with 3 sig figs in the first number. Again, 9.8 is going to be ignored, and then we end up with 3 sig figs in our answer, which is going to be 294 joules. So again, here we added the height of the table plus the height that you lifted above the table, and we find the potential energy with respect to the floor. Let's say if your table was on the 9th floor of some high-rise, and then you want to find the potential energy above the ground level, then you have to add 9 floors plus the 2 meters that you lifted it, and then you can find the potential energy in that case, right? So it really all depends on what's your reference point. So this is, again, one way we can find potential energy just using the equation. Here's another example where we have an archer who pulls on a bowstring with an average force of 240 newtons while drawing the arrow back a distance of 0.2 meters, so 20 centimeters. So let's calculate the potential energy of the bow arrow system. Now, whenever you shoot an arrow, for example, you are putting energy into it with your muscles, right? So you pull on the string, actually putting energy, right? So the energy doesn't come from anywhere. It's like you're just transferring your energy from your muscles into the bow, and the bow acts like a string, like a spring. And then once you release the arrow, all the energy goes to the arrow through the string, and then it makes the arrow fly. So for example, if you pull on the bow without the arrow and you release the string, you can actually break the bow because all the energy that you put into it goes straight into the limbs of the bow and it can crack it. So that's one of the things you should never do with the bow. But anyway, in this case, if you look here, we don't have any work done against gravity, right? We're not talking about gravity here. So the way we can solve this question is we can find the work done to the bow by looking at the difference at the stored potential energy in it. So in this case, we're going to treat it as work. That's going to be the difference in potential energy. So it's going to be our delta E here. So if you remember, this is another definition for work as a change in energy. But in this case, we're just talking about potential energy. So we can add the subscript there for E potential. Now we know that work is also equal to force times distance. So in this case, we can do it in two ways. You can do final minus initial, right? Because delta means, so remember, delta means you have final minus initial. So what you can do is actually split this into multiple steps, and you can show that you will have your final distance here. So let me do it this way. So if you want to show extra steps, you can do it this way. You can show they have your final distance times the force, and then initial distance times the force, so D naught. And then you can plug in the values for each one, and you're going to end up with basically delta D in your equation. So you can end up with this, right? That's what we're showing here, the change in distance really, because the force applied is the same. And again, this is going to be equal to F. If you factor out the F, you end up with this. So again, there's nothing really new here. I'm just showing the extra steps that are not shown in the key. So when you look at the video, you can actually get some more information from it. So here, we know that the change in the length or the way you pull on the bow, the way you draw the bow, is going to be 0.2 meters. So here we're going to plug in our 240 newtons of force. So that's our F value. And then we're going to plug in our final position minus the initial position. So final position is going to be 0.200 minus the initial, which is going to be 0, right? So really we end up with just 240 times 0.2. So if you multiply 240 times 0.2, this is going to be 2 sig figs in the final answer. So we end up with 48 joules. Okay, so this is an example where you can find the potential energy of an object that's not necessarily something that's being done against gravity, right? In this case, we're treating the bow as a spring, and we can find the potential energy by looking at the difference in energies. So initial versus final. Okay, now in your notes there is a little activity. Unfortunately, won't be able to do it, but you can try this at home, and you can do the part that deals with the potential energy. So it's asking you to make a ramp and then calculate the energy of it. So for example, you have to weigh whatever, let's say if you can use a toy car or something like that, you'll have to weigh that, and then if you make your ramp, you have to measure the height of your starting point, right? And once you know the height and you know the mass of the object that you're dealing with, you can find its potential energy. Unfortunately, we can't do this together, but you can try this at home. So for practice, there are some practice questions in your notes package. So section 7.2, potential energy, there are 5 questions. So again, as you go through the questions, if you have any questions on any of them, make sure you post them in the comments on Teams so I can go over them later on.